Hello everyone, welcome to another lecture of the course Digital Signal Processing. In the previous lectures, we have seen what is the Z transform and also seen what is region of convergence. While solving some examples, we have seen few properties of region of convergence. So let us first summarize those properties. So the first one which we have seen was the region of convergence is bounded by poles. Now by saying this, what exactly I mean is that poles are never a part of region of convergence, but if we consider the case of zeros, the zeros may be a part of region of convergence. We have seen few examples in which the region of convergence was of the form of as an exterior to a circle or to the interior to the circle or in the form of a circular ring. So the region of convergence is generally in a form of a circular or annular ring. If we consider the region of convergence of a right-hand sided signal, it is always exterior to the outermost pole. And the same case if we consider for left-hand sided signal, it is interior to the innermost pole. Now for a finite duration signal, we have seen that the region of convergence is the entire Z plane, but there is a possibility that we need to exclude the point of Z equal to 0 or Z equal to plus minus infinity, and this is just because there is a possibility of poles at Z equal to 0 or Z equal to plus minus infinity. Now these were some of the properties which we had already seen in previous lectures. Now let us consider a very special and important property which we haven't seen yet, which is given by, for a rational Z transform, the number of poles are equal to number of zeros. Now what do we mean by rational Z transform? Let's look at that first. Now Z transform for any discrete time signal x of Z is generally in the form of polynomial of Z upon polynomial of Z. And this is what we mean by a rational Z transform. Now in general, this can be written as B0 plus B1 into Z inverse and so on up to Bm into Z to the power minus m whole divided by A0 plus A1 into Z inverse and so on up to An into Z to the power minus n. Now let us take a common B0 and Z to the power minus m from the denominator and A0 and Z to the power minus n from the denominator. Therefore we have x of Z is equal to B0 by A0 into Z to the power minus m divided by Z to the power minus n into this B0 we have taken common, so we have Z to the power m plus B1 by B0 into Z to the power m minus 1 and so on up to Bm by B0. Similarly, in the denominator we have Z to the power n plus A1 by A0 into Z to the power n minus 1 and so on up to An by A0. Now if we carefully observe, this numerator is nothing but a polynomial of Z of degree m. And similarly, this denominator is again a polynomial of Z but of degree n. Now let the roots of this numerator be Z1, Z2 and so on till Zm, and the roots of this denominator be P1, P2 and so on up to Pn. So we can write this x of Z as x of Z is equal to this B0 by A0 is actually the gain which can be represented as G, and we can simplify this factor as Z to the power minus of m minus n into, we have z minus z1 into z minus z2 and so on up to z minus zm, whole divided by z minus p1 into z minus p2 and so on up to z minus pn. Now these z1, z2 and so on up to zm are known as the finite zeros. As for these values of z, this x of z is equal to 0. Also this p1, p2 and so on up to pn are known as the finite poles. And for this x of z tends to infinity. Now by claiming this statement, what we exactly mean is, in general or ideally, this z should be equal, this m should be equal to n. That is, m should be equal to n. But this is not the case always. So we have other two cases, that is m is greater than n or this n is greater than m. So if we consider the first case where the m is greater than n, then in that case, if you look at this exponent or the power of this z, if m is greater than n, then this power will be negative, and in that case there would be m minus n number of poles at z equal to 0. So let's write that. In this case, we will have m minus n number of poles at z equal to 0. Similarly, for the other case, if my m is less than n or the n is greater than m, this power will be positive and we will have mod of m minus n number of zeros at z equal to 0. Let's write that. We will have mod of m minus n number of zeros at z equal to 0. Moreover, there is a possibility that we have poles or zeros at z equal to infinity. So if we have poles at z equal to infinity, it means that at x equal to infinity it tends to infinity, and for the case of 0, at x equal to at x of infinity the value tends to 0 or is equal to 0. So considering all these things, all the four things, we claim that the number of poles are equal to the number of zeros. And while claiming this statement, we are just not considering the finite poles, but we are also considering the poles and zeros at z equal to 0 as well as at z equal to infinity. So the main takeaway of this lecture was, for a rational z transform, the number of poles are always equal to the number of zeros. Let's stop here. Thank you.